So far we have seen that we go for multi-level paging whenever the size of the page table is larger than the size of the frame. Only in that case we go for multi-level paging. Anyway, let's see this. See, this is the diagram implemented using single level paging. Okay, single level paging is the one level of page table we use. We have seen it so far, right? Whatever we have seen it till now, it is nothing but single level paging. Now we are going to see something called as multi-level paging. See, here this is page 0 of process P1, this is page number 1 of process P1, and both these pages are placed in the frame of RAM. Okay, some frame of RAM. You don't need to look into this diagram, but what I want to tell you is this is placed in some random frame of RAM and this is placed in some random frame of RAM. Now we cannot use this address to index into this frame, to index into the process using simple addition, because this process is not placed in contiguous addresses of RAM. They are placed in non-contiguous addresses, right? This will be placed in some random frame and this will be placed in some random frame. So we cannot apply simple addition and index into this page directly. So for that reason, what we did is we took the address of this one and placed it here, or frame number. We took the frame number of this page, frame number in which this page is present, and we placed in an entry. And also we took the frame number in which this page is present and placed in this entry. This is what we mean by page table, right? The number of entries in this page table will be equal to number of pages our process has. Since here we have 2 pages, we maintain 2 entries, right, in this page table. Now this page table is actually placed in contiguous addresses, right? Because this page table will be taken and be placed in a single frame. Now since this page table is placed in contiguous addresses of RAM, we can index into this page table using simple addition. How? See, we already seen it, right? We will hold page table base address. Using this address, we will reach this page table. Fine. After reaching this, we will see the page number in logical address and we will go to the corresponding entry number. For example, in case if page number is 1, we will go to entry number 1. In entry number 1, we will get the frame number in which this page is present. And then we will go into the corresponding frame. We will go to the corresponding frame and then using the page offset field, we will get the exact byte within that frame, right? That is what we have seen it. But this is not always possible, okay? Sometimes what might happen is the page table size might be larger than the size of the frame. See this here. Let us assume that we will be able to place, it is just an assumption, okay? We will be able to place only 2 entries in a page, in a single frame of RAM. See, this is what we mean by frame of a RAM, right? Now in this frame, let us assume that we can place only 2 entries. Number of entries in the page table depends on 2 things. One is page size or frame size, and another one is page table entry size of a single entry. So frame size divided by entry size will give us the total number of page table entries which we can place in a page, right? Let us assume that we have somehow found out that we can place only 2 page table entries in a single frame. But here we have 3 pages, right? We have 3 pages. So in our page table, we are supposed to maintain 3 entries, right? But we have already seen that we will be able to place only 2 entries in this page table. This is our assumption. So what we did is we took the frame number in which this page is present and we placed it here, right? And we took the frame number of this page and then we placed it here. Now we cannot place the frame number of this page over in this frame because we cannot place more than 2 entries. So what I did is I took another frame in the RAM and I created an entry. This entry will hold the frame number of this page. Okay. So this entry is holding the frame number of this page. This entry is holding the frame number of this page. This entry is holding the frame number of this page. Now after placing this entry, we have free space, right? See, we have only 3 pages. In case if I would have had 4 pages, I could have created an entry for the 4th page over here. But since I have only 3 pages, I can't do anything about it. So I will leave this space as it is. Okay, this is again internal fragmentation. Okay, this is again internal fragmentation. Fine. So why I have placed an arrow mark over here? See, these things are acting as pointers, right? See, what is meant by pointer? Anything which is holding the address of something is called as pointer in computer science. Okay, we have something called as pointer variables in C programming, which is not very important here. A variable in C programming, what we see, I'll give you just overview, okay, of C programming. In C programming, any variable which is holding the address of another variable, we say that as pointers. Okay, here what is actually happening is this is holding the address of this frame, right? This page is actually present in some frame. Fine, we are able to reach this frame using this entry, right? So this entry is acting as a pointer to this frame. Okay, this entry is acting as a frame to this entry is acting as a pointer to this frame. Similarly, this entry is acting as a pointer to this frame. That is the reason I have placed the arrow mark over here. Fine. Now can you index into this page table? See, all this we say that as level. Okay, this is level 1, this is level 0, this is level 1, or this is level 0, this is level 1. That is not important. Now let's see this level. Okay, we have not come to this level, we have not seen what this is. We'll see that later. Now what I want to do, we have two page tables as of now, and let us assume this page table is placed in some frame in RAM. Similarly, this page table is placed in this frame in RAM. Okay, which means they both are placed in non-contiguous addresses in the RAM, both these page tables. Fine. Now my question is, can I index into this level of page table using simple addition? I cannot do this. Why? I cannot do this, right? Why? Because these pages need not be in contiguous addresses in the RAM, right? Which means this page can be placed in some random frame in the RAM, whereas this page can be placed in some random frame in the RAM. So in case, as you know, in case if something is present in non-contiguous addresses, we cannot index into that using simple addition. So we cannot apply simple addition over here and then index into this level, into this page table. So what we do is we create one more level of page table. Okay, we create one more level of page table. What we do now is we take, see, this is also placed inside the RAM, right? This is a page which is placed inside a frame of RAM. This is a page which is placed inside a frame of RAM, and so is this. The same is what is happening here. This is placed inside a frame of RAM. This is placed inside a frame of RAM. So there will be a frame number in which this page will be present, right? That frame number I am going to place it here. Okay. So obviously what is actually happening is this entry is actually pointing to this frame. Okay. Similarly, this page table or this page will also be placed in a frame, right? So that frame number will be placed over here. So this entry is going to act as a pointer to this page. Okay. Now tell me whether can I index into this page table using simple addition? I can definitely do that. Why? Because this is placed in contiguous addresses, right? See, this will also be placed in a single frame of RAM. Now if I take this page table and if I place it in a single frame, let me assume that I am placing it here. Okay, I have placed in a single frame. In case if I place it, a complete table is placed in contiguous addresses in the RAM, right? So definitely I can apply I can index into this page table using simple addition. Okay, now how will I do that? That is the